Hi, I'm Ronen Botzer. I'm the director of product at Aerospike that deals with core database, the clients and tools. I started out at Aerospike in June 2014. I was first an engineer and later a solutions architect before moving to product. So what's on the agenda for today? We're going to talk about what are Aerospike expressions, go over filter expressions, the expression execution model, operation expressions with examples, expression composition. We'll talk about variables and control structures, and then a little bit about debugging. So what are expressions? An expression is a syntactic entity that can be evaluated into a value, and that's in contrast to a statement which carries out instructions and doesn't return a value. An expression can contain variables, operators, and functions, and it returns a value, typically a primitive like string or integer, but it could be something complex like a list of integers. So here's a quick example of expressions. We have 10 modulo 3, which evaluates to 1. We have the next one has two sub-expressions. One of them is max, and we have a list of arguments, and out of them, it evaluates to 500. And then we have on the right-hand side, the minimum of a list of arguments, and that evaluates the 4, and then we have 500 minus 4, which evaluates the 496. The last one is very Aerospike-like. We're going to take a get by rank on a specific value range of a list. So the value range is all the numbers between 10 and 20 out of a specific list, and that selects 15 and 16. And then the get by rank minus 1 means the highest rank, which is 16. So that's how expressions evaluate. So Aerospike expressions is a domain-specific language for comparing and manipulating record bins and metadata. It was created by our director of engineering, Kevin Porter, and our principal engineer, Shu Chen. Aerospike expressions is strongly typed, functional, with a design that's influenced by Lisp. Now, bin data and record metadata that is accessed inside an expression is immutable. That means that changes always happen on an ephemeral copy. For example, if you're reading a bin, you always get the same value, which was its value at the beginning of the operation. The copy is released when the execution of each sub-expression is complete. So that gives you an idea of the scope of every sub-expression. Now, Aerospike expressions use a Polish notation, prefix notation, basically, for its syntax. So here are two quick examples. If we're doing 4 plus 3 in infix, in prefix notation, it would be plus 4 and then 3. It's the operator, operand kind of structure. And if we're doing, we want A equals 1 and B greater than 2, this would be how we'd write it out in PN syntax. Aerospike expressions are used in filter expressions, which were introduced in the 5.2 release, Xdr Filter Expressions, which was added in 5.3, and then operation expressions, which are new to Aerospike 5.6. There's a quick cheat sheet of the operations that we can use inside of expressions, and they basically cover all of the existing data type APIs plus a bunch that deal with the record metadata. So we have comparison operators, equal, less than, etc. We have logical ones like and, or, not, and exclusive. There's the new addition in 5.6 of declaration and control, which again, if you are familiar with Lisp or Lisp variants, this would look very familiar. There's a new arithmetic library of operations. In the past, Aerospike really just had increment, on integers. And now there's this wide list of arithmetic that we can perform on, numeric and data type mostly. There's record metadata, which existed before, but is still around. We have the record storage data, checking if certain bins exist, if, checking on their type and on the key. And then, like we said, there's the full list operation API. There's bitwise operations on blobs. the very extensive map operations API, and then the ones that deal with hyperloglog and hypermin hash. So first, let's talk about filter expressions as a concrete implementation. These are used to select records based on the value of a Boolean expression. They replaced predicate expressions in the 5.2 release. Now, predicate expressions have been deprecated since, and now we're at the halfway point until they get removed. The plan removal is November 2021, so you still have time to transition your code off of predicate expressions to use filter expressions instead. And filter expressions really is a superset of predicate expressions. Filter expressions can be applied to scans and secondary index queries, so things that return multiple records. They're also applied to specific types of scans, which are the background operations in UDFs. These are write-only operations that happen in the background to every record in a set or a namespace. They're also used to filter single record expressions like standard reads, writes, multi-operation transactions, which is the operate command in most of the clients, and then UDFs. And of course, the batch reads. We can use filter expressions to filter out records that don't fit a certain criteria out of a large list of keys. And again, filter expressions can use either metadata functions or data operations to evaluate to a true or a false decisively. Something to note is that these are only happen when the record actually exists. So if the record doesn't exist, we never actually run a filter expression. So don't expect it to really be like an if then else kind of behavior. This really is something that filters out existing records. So the first thing we're going to go over is examples of scanning with filter expressions. There's a repository that is associated with this summit talk, and I'll give you the link at the end. And in this case, we're going to run a script called, Python script called scan filter. So it's going to generate a bunch of records, and these records are going to follow this structure. First thing, the left-hand side here is the key. The namespace is called summit by default. The set name is scan filter. And then the user key is just an integer. Now there's also the record itself is, its bins there's one bin called num, and it has the same exact integer value as the key. And we're going to leverage that later. So the main thing we're going to do is we're going to generate just 2 batches of keys, 0 through 9. We're going to wait a second and then do another batch, 10 through 19. All the even records are going to have a TTL of 1 hour, and all the odd records are going to have a TTL of a minute. Now, I'm going to run this a bit later because some of these are kind of time sensitive. So first I'll talk you through this, and then we'll run the example. One thing to note is that out of the box, Aerospike since 5.0 is not configured to act as a cache, but rather as a database, meaning we turn off TTLs. Because in a standard RDBMS, if you insert a record, it's there until you actually delete it. The application or a user deletes it. So this can be turned back on, but until you do that, TTLs will get rejected by default. So what we're going to do is for this specific namespace, Summit, I'm going to go and quickly change a couple of things. One of them is set the NSUP period from 0 to 120 seconds. So every 120 seconds, the namespace supervisor wakes up, checks to see if records are expired, and tosses them out, does the cleanup for us. So that's one of the things we need to do. The other thing is we're going to assign a default TTL of 2 hours. This will be convenient in this example. So I'm going to run that too. And I'm going to get ready for running the script. Actually, this is going to be this one. So let's just talk about it a little bit first. So first thing we said, we're creating these 2 batches. Then immediately we're going to try to find all the records that were written the last second. So there was that pause, and we only expect the second batch to show up here. And the filter expression is pretty simple. We're looking for everything that has a since update time of less than, greater than 1 second. In this case, it's 1,000 milliseconds is the input that since update time is expecting. And the next thing, we're going to touch all the records that are expiring in the next 30 minutes, whose num bin is odd and equal to less than 10. Again, there's 2 batches. Each batch has even and odd ones. We're going to look for the odd ones in the first batch. And we're going to do this with the following filter expression. We're going to look for if there's an integer bin called num, and then we're going to check that its value is less than 10. We're also going to check that, using the arithmetic operation modulo, we're going to check that its value modulo 2 is equal to 1, so it's odd. And we're also going to check a bit of metadata, which is that the TTL is less than 30 minutes. And in this case, TTL operation expects a value in seconds. So we're going to compile that and we're going to pass it into the scan. The scan is going to run on our summit and this set that we expect. And the background operation is going to be to touch the records that pass the filter. If you remember, I'm not giving it any specific touch value, so it'll just be set to the default TTL of 2 hours. The thing we're going to do after that is look for all the records that are expiring in the next minute. And this is why, by the way, I'm going to run it all together later, because the time it takes me to talk, all those records would have expired already. So again, this is a very simple filter expression. We're looking for TTL, the time to live being less than or equal to 60 seconds. This one expects seconds. And we're going to do a regular scan, so the returned records will be the ones that pass this filter. After that, we're going to touch the records that are expiring in 30 minutes that have an odd user key and a value of more than 10. So that's the other batch. And we're going to touch it in this case. So it's very similar to what we had before. And it's, again, going to run in a background operation. So let's run that right now and see what happens. So first batch is being created. Now we're going to wait a second and create another batch, and it's going to immediately scan for those records that are older than 1 second. So we found them, and it's the first batch really that shows up. Then we're going to extend the TTL. Oops, I made a mistake. I talked too long. let me run this again. Now I'm going to show the record, and you can see that we only get the records in the later value, in the later batch, because we extended the odd ones between 1 and 9. And now we're going to check for, we're going to extend the other guys, and now you can find all the records that have, we're going to look at all the records, and you can see that they've all been extended. Some of them are around an hour, but some time has passed. Some of them have been pushed to 2 hours. Those are the odd ones. Okay, so that's just what we completed using those filter expressions. Now let's continue. So quick digression about these terms that we use at Aerospike: scan versus query. So every record, every object in the namespace is automatically indexed in the primary index. Okay, it's kind of like a primary key on a table, but in this case, it's for all the data in the same database in our namespace. This index is the digest, which is the unique 20-byte object identifier. And the thing to remember is that the primary index is actually broken up by partition. We have 4,096 logical partitions in the namespace, and each record gets an roughly even number of partitions on it. Each partition locally on the node has the partition actually split into sprigs, which are little RB trees. And this is how we find the record. We hop to the correct sprig very quickly and deterministically, and then we just walk that sprig to find the record in there. So to get all the records in the namespace, Aerospike has to perform what we call a scan. It's very similar to, the name comes from Like if you think of an RDBMS that has its query optimizer, like the thing that's scheduling the query. If, for example, the table is too small and it decides to not use the indexes, it's going to tell you when you look at the query execution plan that it's going to do a full table scan. So this is sort of a similar term, and that's where that word scan comes from. A developer can apply a filter expression to a scan. So the filter expression really acts as the where clause here, and that's one way we can query the data. Okay, in most of the clients, this is just the query class without passing it a specific index to use. So if you don't pass it a specific index, it'll turn into a scan. It'll use the primary index to find all the records in the namespace or the set that you provided. To index by any other criteria, we need to specify like a data type and a bin name that we want to index, and you build the optional secondary index on it. And you can also apply a filter expression to a query, which is what our term is when you are using a secondary index. The 5.6 is coming out with a new feature called set indexes. And what that is that all the records are going to have a set value. Well, they already have a set value, and now it's going to be automatically indexed. If you choose to use this feature, it'll be automatically indexed, similar to how we automatically index the digest and the primary index. Here we're going to automatically index the association between the record and the set, which means as long as you're not using one giant set that covers the entire namespace, you should see big performance improvements on finding all the records in a set that happens to be sitting in a large namespace. So, if you're using something like Presto, for example, any type of SQL-like query is always going to be a select star from table name. Now that all the records in that quote-unquote table are going to be automatically indexed, which should speed up querying or scanning a specifically just to walk everything in the set or table, if you want to use that terminology. So from a developer's perspective, these are both forms of querying, and the filter expression is what acts as the where clause. So now let's go over examples of single and batch operations that use a filter expression. And this in the repo is in the Python script messages.py. So here we're going to add a batch of records with the following format. It's, again, the summit namespace. The set is messages. The records have a user key that is an integer. And they're all going to have two bins. One of them is a string value in a bin called message. And then we'll have a list in a build called access. And you can see here that there's a series of messages, and they have different access characteristics. So in this model that we're using, if the access list is empty, this means that the message is for the public. Anybody using the system can see it. If the access is a list with just the username, that is considered to be a personal message. It's like a note to yourself. And if you have a access list that has the username plus a bunch of other users, that is meant to be a private message that is shared with one or more people. Now we're going to apply filter expressions to single record operations and batch rate operations. So first thing, let's try to get the first message using a public message filter. So we're building a key. The key would be, using the user key integer 0. And we're going to use this filter expression, which basically checks the size of the bin called access, the list bin called access, and checking that it's 0. And if it's 0, that means this is a public message. So we're going to apply that to message 0, and you can see that we're getting it back. The next thing we're going to do is use the same exact filter to look for a public message and apply it to record number 1. And if we go back, look at record number 1, that is not an empty access list. So what we'll get is the explicit exception with error code 27 that says it's been filtered out. So you know the difference, on the application side between you can't find the record, this record doesn't exist, versus the record, reading the record, the operation on the record was filtered out because of the criteria that you passed in the filter expression. So let's go ahead and do that. I'm going to populate them. We're going to look for message 0 and see if it's public. And yes, it is. And you can see the access list is empty, and then message ID 1, and it gets filtered out. Next, we're going to find all the messages with using a batch read and a filter. So the first thing is it's the same type of thing for public messages, the exact same filter as before. And in this case, we're going to build a key space of all the keys between 0 and 7 in this specific namespace and set, and apply this filter. And what we expect to get back is really just the public messages like this. So, and you can see that's how we got what we expected. Now let's stop for a second and talk about the let construct, which is what we use to do variable declaration and use. Again, if you're familiar with any Lisp variant, closure, etc., this exists there. So this is, you can define any number of variables that you want to use. They're all going to be pairs of variable name and variable value. And at the end, there's going to be an expression that all of these can be used inside. Okay, so these variables are for the scope of the expression that we have at the end. And in order to use them inside the expression, we use var on the variable name. It returns the value that's like this whole construct returns the value computed by the expression at the end. And this is useful when you need to repeatedly use the same calculation, and it might be kind of a heavy calculation. So it makes more sense to declare it as a variable and then use it in the expression multiple times, and not, spend the CPU of calculating the same thing over and over. So what we're going to do here is find all the personal messages from a batch of records. And like we said, personal messages are ones that we only have a single username in the access list, and it happens to be the username of the user. So if you didn't notice, these are messages that come from the script for the movie Clueless. So we have two characters here, Cher and D. And in this case, we're looking for all of Cher's personal messages. So it's the same, it's a similar filter to what we had before, but we're going to do this in a let. So the first thing, we're defining a variable called access size. So this is just like a bin name, but we're actually choosing a name for it. It's not restricted like bin names are to 15 characters. And the thing that we're going to be assigning as a value is calculated in the sub expression here, where it just checks the list size of the list bin called access. Now the expression here is we're going to check for access size is 1, and for the first position in the list, the index 0 is Cher. Okay, so let's run this. Actually, let's see. I think I have this. Yeah, I have it here. So we're going to do the batch read, and what we expect to see back is that one message came back, the one personal message. And it's as we expected. So now we're going to use an alternative filter expression to get personal messages. And the reason I'm doing this is, like I said before, the real reason to use a let is to save on pretty expensive calculations being repeated. Getting a list size is actually very lightweight. It's a bit of metadata for the list that does not require any kind of heavy lifting. So we're just going to replace the let with just direct access. And we're going to check in this expression whether the list size is 1 and whether the index 0 in this list is a username called share. And that's just makes it more concise, and there's no real reason to use that. So we're going to run this, and we got what we thought we were going to get. Now let's find all the, skip this. Let's find all the private messages. So private messages will have 2 usernames in them or more. And one of those has to be the actual user, because we don't want to give a user access to somebody else's private messages. So this is the filter expression. And we get back, when we run it, we get back the messages between share and D, and that's it for applying filter expressions to batch operations. Last thing is we're going to find all the private messages that are less than 5 seconds old. And here, because we've been talking so long, this is probably not going to work. So I'm going to skip that in the actual execution. You can run it yourselves later and do it a little faster than I'm doing it now. But let's talk about the filter expression being used. So we're going to check that for 3 things here in the end. We're going to check for a since update time that is less than 5,000 milliseconds. We're going to check for a list size that is 2 or more, greater or equal to 2. And we're going to check that inside that list, one of the values, so list get by value, is share. We want to make sure that when we return the count, we see share show up once. So after a short pause, this filter matches no record as expected. And this is an important point to make. The only thing that happens here is the metadata fails. We immediately fail on since update time is less than 5,000, because we've been talking for quite a while and it's going to be more than 5 seconds old. And because of that, we don't even go to do the checks on the actual record data. So we don't have to read, Aerospike doesn't have to read the record from storage because the metadata phase failed, so we don't continue to execute the rest. It's pretty efficient that way. So you can see nothing came up for that is older, less old, whatever, newer than 5 seconds. So we're going to digress really quickly to talk about the filter expression execution model, because this governs what we just saw. Metadata lives inside the primary index. Every object has a 64-byte entry in the primary index, and that's where the metadata is kept. The record data is kept in the storage device for the namespace, and that could be an SSD, it could be persistent memory, it could be RAM, etc. You get to control that, but it's consistent for all the records in the namespace. Now, if an expression can be resolved with metadata, there's no need to perform access to storage. So to gain this performance advantage, Aerospike expressions, when you're doing filter expressions, use a 2-phase evaluation. The first phase is the metadata phase, and it starts with all the storage data evaluated to unknown. Okay, we just plug unknown for all the sub-expressions that deal with storage data. And then if the metadata phase evaluates to false, then we don't really need to move on, because we already know it can't evaluate to true at the end because this component is false. So that one is done. If the metadata phase evaluates to unknown, right? If we're not sure if it's true or false, right? Because it didn't resolve to anything conclusively, then we're going to move to the storage data phase. If the metadata phase evaluated to true, then the operation proceeds. We're good to go, and we only load the record if it's needed. So only if you're actually looking for something in a, return a bin, then we'll do this. If you're returning just metadata, then there's no need to do that. Now, if we got to the storage data phase because it was unknown, then it's going to load the record from storage. It's going to execute the expression a second time, and this phase always evaluates to true or false. because we already know what the metadata is, and now we know everything about the storage data phase. So Xdr filter expressions were added the following release in 5.3, and they allow you to optionally filter records to specific destinations if you're using cross data center replication. This gives us fine-grained control over data distribution. You get to choose exactly what data goes where, which will save you on the cost of bandwidth and storage at the destination if it doesn't get, every update going to it. Filter expressions, XDR filter expressions are dynamically defined per namespace per destination using basically an info command. So there's an info command, XDR set filter, and you give it the expression as base64 encoded. All the clients, or most of the clients, should have the ability to convert an expression to base64. For example, in Java, this is what I'm displaying. So I just showed you how you set it on a DC for a specific namespace. And you can also remove it by just assigning null instead of a base64 encoded expression. And if you want to see what the filters are on the namespace and destination, you call XDR get filter, and it'll look something like this. It actually returns it back as a kind of like human readable language. And that gives you an idea of like what it was that somebody in your company attached. So let's move on to operation expressions, which are brand new. Operation expressions extend read and write bin operations with the ability to compute values based on record metadata and bin data. That makes sense. Use computed values as arguments to existing operations. That's something completely new. Extend the bin data type APIs through composition, and I'll give you an example that's very cool. And they also support atomic cross-bin operations that previously were only available in UDFs. So if you want to read one bin and use it when you're writing or reading another bin, that's something you can do. In the past, operations were very tightly separate from each other, and there was no way to go cross-bin when you're trying to do operations. So where filter expressions were used to determine whether the operation on a record happens or not, the operation expressions extend the actual record transaction. Okay, so this comes after the filter. If there is a filter and it passes the filter, then we can get to operation expressions. And these are used inside the operate command. So any place you can use the operate command, which is single record transactions or background scan operations, you'll be able to use operation expressions. So we're going to use this simple op example Python script to show you how read expressions work. So first thing, you can get the record metadata back as a bin. In the past, you guys know that we added last update time after the fact, and it was not available unless you used a predicate expression or if you use the UDF. There was no way for a regular get to know what the last update time was. So here, what we're going to do is we're going to declare there's kind of two ways to get the data. One of them is an absolute date time, and one of them is relative. It's just a number of seconds or a number of milliseconds since the last update. So we're going to use both of those. I'm creating an expression for each. And then we're going to create a transaction, and a transaction in Aerospike is launched by the operate command, and it has multiple steps. Each one of them operates separately, but they're all in one transaction. They're atomic. They will roll back if any of them fails, because again, we're working on an ephemeral copy, so there's no problem rolling back the data. And let's see. So the first thing is a standard operation that we always had, the ability to read the bin. So we're going to read a bin called us. And then we're going to do two read expressions. We're going to call the since update expression that we assign to a variable, and then the last update time one. And this gives us, again, two views of the same record metadata. Now, you can see that these are mixed together, right? The other thing to point out is that similar to an as in a SQL statement, select statement, that is, where you can say, I want a column, but I want it with a different label. We can do the same here, where we say, I want these values back as a specific string, as a label for them. So let's run that really quickly. And now I can see that we got back the last update time. We got this bin, us. We got the since update is 1 millisecond. And then the last update time gives you in nanoseconds the Unix epoch value. So converting those, into normal speak, it just gives you the time that this ran. Now we're going to look at some cross-bin operations. So let's say we have a record that has 4 bins in it, A, B, C, and D. The bins A and B are both lists of integers. C is an integer value 27, and D is an integer value. And I'm going to use the let construct here. So I'm going to define a variable called combined, and that is going to take, going to append the items from list A to list B to B, okay, and put those together, the result of those in a variable called combined. Then I'm going to define a variable called combined min, which is going to take the combined variable, if you look all the way to the right, and it's going to do a list by rank operation on it and get the lowest ranked, the 0 rank element in it. And we're going to declare another variable called combined max, which basically, again, takes the variable that we just calculated called combined, and it's going to find the -1 rank, meaning the highest rank for it. And now that we have those 3 variables defined, what we're going to do is we are going to take the difference between the max and the min and return that. And then we're going to do, I'm declaring another expression, which is finding the min of bins C, D, and E. And you notice there is no bin E yet, but this is what it does, what this expression does. And now let's look at the operations in this transaction. So first thing, we're going to do a write expression into a bin called E, running the calc operation expression that we just defined. Okay, you can see how it's up here, and we put this expression in a variable called calc. So that's going to go and get written into a bin called E. Then we're going to read bins E, D, and C, just display them back. And we're going to do a read expression called, this expression called get min, and we're going to return that in a bin named called min. And the next thing we're going to do is we're going to create another quick expression called the sum of D and E, and that's going to be the bin name that we return. And it's just adding bin D and bin E. And I'll remind you, there is no bin E right now, but it's going to be created in the first operation of this transaction. Now let me run this, and that is as expected. And now let's look at expression composition. Now we just did one of those, but let's get a little more fancy. There's a Python script called exp composition, and we're going to run it shortly. So this thing has a large list of integer values in a bin called n. And what we're going to do is, let's look at it from the bottom up for the unordered slice. What we're trying to do is we're trying to create a new functionality that looks like a Python slice or a Ruby slice. So, let's assume that we're going to do a get by value range. We're going to find all the elements that have a value between 10 and 90. And then we're going to return the first 4 of them. Okay. Everything between 0 and 3. So we are gonna, if you look from the bottom up, we're gonna get the list. We're gonna get n as a list bin. So this is gonna return everything in n. Then we're gonna pass it to get by value range. We're gonna find everything between the values of 10 and 90. And then we're gonna pass that result to get by index range. And we're gonna get, an index is the position, right? So we're gonna return 0 to 3 back. Similarly, we're going to also do an ordered slice. So this was on the unordered list, and you can see n is an unordered list. But what if we wanted to actually get back this in an ordered way? So we're going to get the value of bin n, which is a list. We're going to pass it to value range, find everything between 10 and 90. Then we're going to call sort on it. And on the sorted list that we just have right now, this return a list and we sorted it, we're going to get the top 3, or sorry, between 0 and 3. And sorry, the last one is exclusive. So this is what it looks like. We have a transaction that is going to do a list get by value range, just so we can see what is actually returned from the inside. So we're just running that and finding all the values between 10 and 90. Then we're going to call a read expression. We're going to call unordered slice, and we're going to put that in a bin name called unordered 0 through 3. And then we're going to do another read expression and call the other expression called ordered slice on it. So if you look at the left side here, this is actually what the value range returns. Unordered just basically gets the first 3 elements here, which is 78, 10, and 15. And ordered will first order them. So the order should come out to be 10, 15, 21, 45, 55, 66, 78, and we're going to get the first 3. And that's exactly what we expected to do. And we created new functionality here by composing these operations together. Okay, and just to show you that it didn't change, okay, what we did here is I wanted to show you that that ordered O3 and unordered O3 don't show up as bins actually in the record. These are really just read expressions, and they return what looks like a bin, just like we can return a fake column in an RDBMS from certain expressions. So you can see how the record didn't really change due to read operations and the read expressions. Okay, so let's talk a little more in depth about the cond structure, which is conditional evaluation. A cond is similar to a switch statement. It's basically a series of condition and action associated with it. So if the condition evaluates to true, then the associated action is evaluated and returned, and we're done. We don't move on to keep evaluating things. We'll skip over all the other conditions as soon as we find one that is true. If no conditions are met, we have a default action that is evaluated at the very end. This default action can be an explicit unknown. So if you don't want to return an actual value, you just want to kind of short circuit the expression, you can explicitly return an unknown. Now, in general, any action can evaluate the unknown, and that could, most likely would, abort the operation expression. When that happens, you will get back an error code 26, Aerospike not applicable. In a transaction, you can suppress this using one of the no eval policies. I think Python has an explicit no eval policy for reads and for write expressions separately. If you're in a filter expression, don't use unknown. Instead, the default, and you want to exit, you want the default action to return false, because if you remember from the execution model, an unknown will cause it to go into the data storage phase. So you would rather return a false. if you are using, if this is an operation expression, that you can return unknown. So now let's do something more complex, and we're going to calculate the churn in a youth soccer team using operation expressions. This is a Python script called roster.py, and we're going to start with the roster on this team in 2016. Now, the reason I have this information to use is because I volunteered with this team for many years. My son is one of the players. He's graduating as a senior and playing his last season in high school right now. But this is actually the list of kids that, every season you would have kids moving in and out, and this will calculate the churn. Now, for churn, basically, we're going to count any new player that is added in or leaving the team. Those are all going to be counted once for each player going in or out. So let's look at the cond expression. We are going to look at the bin called roster, and we're going to check if it's a list. That's the first thing we do. And if it is a list, we're going to get the list size on it. If it's not, then we're going to return 0, meaning if it doesn't exist, we're going to count it as 0 to start with. The other thing that we're going to use another conditional value here, another switch statement, which is going to basically, inside of an add, we're going to look at if there is a bin called churn, and if it's an integer, we are going to use its value. And if it's not an integer or it doesn't exist, we are going to use 0. We're going to just start with no churn because we have a 2016 roster. And the actual expression that we're going to use is we're going to use the absolute value from the arithmetic operations. And then we're going to find the difference between the size of the roster before and after. The before is going to be in a temporary bin. So I'll show you in a second how we're going to use that. And we're going to find the absolute value of it. Okay. So that's what this expression does when we calculate churn. So we had a list for 2016, and now we have two things we're doing. We're going to remove 3 players, and we're going to add a whole bunch of players. Some of them might be already on the team, but we're going to use a list policy that says this is a unique list. So it's an ordered list, and the values are unique. So we're going to ignore adding ones that are already there. So the first thing we're going to do is we're going to call the filter. We're going to call the expression, sorry, the operation expression called current, which, let's go back and look. It finds what is the size of the roster, if it exists, and just puts it writes it into a temporary bin called temp. Then we're going to add all the new players. And the list policy, if we look at the code really quickly, that's going to go and open the roster. So where is my list policy? Sorry. The list policy is basically going to be, we're going to only add unique elements. We're going to, this is going to be an ordered list. We're going to write all the partials. So anybody that already exists is going to be rejected, but any new players will make it through, and we are not going to throw an exception on this. So even if there are collisions, which a unique list usually throws an exception on it, here we don't fail, we accept the partials, and we just move along. So let's go back. The second operation in the transaction is we're going to add the items with that list policy. Now we're going to calculate the churn, okay, after adding the players. Then we're going to get the size of the current list and put it in temp again with a write expression. And now we're going to remove by value list the list that we wanted to remove. We're once again going to calculate the churn. And then we're going to clear out this temp bin. Okay, we're going to just throw that out because we don't want that to stick around. And we're going to return the churn and the roster. Okay, so this is the result of running this on the 2017 roster. The new roster is up to date after we removed and added players, and the churn is 8 because if you remember, we dropped 3 players and we added a whole bunch more. So this year we had a churn of 8. Now we're going to keep running this really quickly. I'm going to start from the top because we have multiple phases here. We're starting in 2016 and moving all the way to 2019. So let's track. We start with initializing the 2016 roster. Then we update with the 2017 roster. We remove 3 players. We add this big list, and we get that churn of 8. Now let's do the 2018 roster, where we're going to remove 4 players, and we're going to add 1, 2, 3, 4, 5, 6, 7. Some of those might already be in the list, and we get a churn of 17. That was added to the 8 before. So between 2016 and 2017, we had a churn of 8. Between 2017 and 2018, there were 9 more players that churned. And let's do the 2019 roster. We're removing 3 of the players and we're adding a whole bunch more. And now we have a much larger roster. And the churn cumulatively has moved up to 28. And just to go back, we use these fairly complex operation expressions and use them together with right expressions in order to do these calculations. And this happens in a transaction, which really is multi-operations on a single record. It's isolated, it's atomic, and it's durable. Okay, like this is the only reason I'm not using C is because Aerospike doesn't have a schema, so there's no schema to compare against, but otherwise it's exactly what you expect it to be. And the last thing I want to go over is really how to debug expressions, because in general, Aerospike, the server only sends back error codes and not error messages. When you do see error messages, those are actually just filled in generically by the client. So you have an idea and you don't have to look it up. The specific information about any error is actually in the server log. So if you're a developer and you're developing, an application that is talking to Aerospike, you want to be checking your server logs for, warning level messages to see really what happened. But you could also create a lower log level of debug or even detail if you really want to get a ton of information. And you can use Aerospike in order to create a different logging context. So we can send the particle and the expression context to a different log file that has a different log level to it. And if you look at I have a link for this, but if you look at basically our technical documentation and you look under configuration, there's going to be a whole section about how to configure log files. And we're going to send those, and you will see that operation expressions result in error codes such as, error code 26, that it's not applicable, and the messages will look something like this. So in summary, expressions are very expressive. They are very high performance alternatives to UDFs. And if you have used UDFs in the past, you should really look at expressions and consider whether you can replace them, because they're going to scale better, they're going to run much faster. Really, they are a much better alternative. They can be used with filter expressions. They can filter XDR shipments. They can extend read and write operations. And there's going to be more that we do with expressions in the future. So we're going to continue to build on top of Aerospike expressions for more functionality in the server. So what should you do next? First thing, if you don't know yet, we have a free Enterprise Edition evaluation that you can use. Anybody can download a full-featured single node feature key file, be able to run a one-node cluster in development that has all the features in it. You want to use Presto, you want to use Spark, you want to use Kafka, you want to use XDR between 2 single nodes for your proof of concepts or prototyping. That's something you can do by signing up. And all you need to do is just put in an email. You get an email back that has the feature key for this Enterprise Edition evaluation. You get access to Aerospike Academy with all kinds of training classes for developers and other instructions in there. That's pretty cool. You can clone this repo. It's right there under the Aerospike examples org, and you can run these Python scripts yourself and look at the code and tweak it. You can visit the Aerospike Developer Hub, which actually has a ton of Jupyter notebooks that explain how to do all kinds of different things in Aerospike, from modeling to how to use the data type operations, etc. It's very useful for developers. You can read, obviously, the technical documentation at docs.aerospike.com. Subscribe to our developer newsletter called the Aerospike Stand-Up, which will give you, every 2 weeks, you will get a update on, developer blog posts and new releases and new changes to the documentation. And then these are the developer blog posts. There's one on Medium and one on Dev, and you can look at those. So thank you for listening, and let's see if anybody has any questions.
So thank you, Ronen. That was great to go into that much details and all those great examples that I'm sure a lot of folks will be re-going over once we share the slides. So let's see, we have a couple of questions, and please don't hesitate, ask as many questions as you have. And if not, you know where to find us if you have more questions. So one of them, I think, was answered at the end of the presentation.
Yeah.
About how to track bad queries. So I think there were some good details there about changing log levels, etc. There's one about are you able to time expression versus filter? So I assume this may be because of some confusion on the renaming of expressions and filters.
Could be. I mean, if we're talking about predicate filters versus filter expressions, I mean, we don't really have a stat and we don't really have a comparison of them. What you could do is you could just benchmark the two against each other. But just to remind everybody, predicate filters, we are at the 6-month mark for the deprecation. So you have another 6 months to remove it. So please take a look at this. These are more efficient. We know that, but I don't have benchmark for people. So you can benchmark it internally. And if you're an enterprise customer and you see that it's not the case, or in general, if you're in the community, just let us know, okay, and we'll take a look into it.
Great. And this, I assume, so I attended a talk yesterday from Sunil on expressions within Xdr, and I assume the same thing applies here, which is no matter how you write your expressions, the Aerospike server is smart enough to first apply the
metadata phase, yeah.
So I don't know if you have anything to add on that front.
No, I mean, if you involve metadata, it is going to first try to toss out the records that don't satisfy that, and then there's no need to even read the record. Now, if you're in memory, of course, this is less of an issue, but if your data is on a device like SSD, PMEM, all flash, you probably want to consider using metadata in your where clause, basically, in the expression, filter expression.
Right, thank you. So one more on rack ID. So I'm trying to wrap my head around. So is rack ID available in metadata for filter or Xdr?
No, there is no metadata for rack ID, so it doesn't know that it's on a specific rack. But that's not necessarily a bad ask. I don't know about the implementation details. I'll pass it along. But definitely, yeah, that's an interesting concept. I don't know though if we are aware of it like deep down in the guts of the machine.
All right, thank you. So I have a couple of questions, unless there are more. So we'll see. I'm still monitoring if there are more questions. So yeah, can you touch on expressions versus UDF? So I think expressions are better. Can you explain a bit why? Yeah,
so UDFs are, if you guys know right now, they're in Lua, and they have to execute on a on a Lua interpreter, and this is Lua JIT, so if the same thing runs on over, it will eventually get better at its execution, but it is very limited in terms of, first thing, the API, because the list and map API inside the UDFs was created before we had the list and map API for the server. So it's not the same, and it's missing a lot of functionality. You don't have access to hyperlog lock operations, the bitwise operations, all these things that are part of the, you can't compose them like you can, like I showed. So UDFs are really limited in terms of their functionality. Now, we would like to rewrite UDFs at some point, but it's not a top priority. So whatever you can do in filter expressions is going to perform better, it's going to scale better, and it's going to give you full access to the entire API that we have, right? All the APIs of all the data types and all the metadata. It's very nice for that. So I think the majority of UDFs can be converted to operation expressions and filter expressions. So, take a look at that, and your essays will be happy to help you.
All right, thank you. So I think we may have time for one last quick one. So is the presentation available to download? Yes, so this will be available. I'm not sure exactly when, so it will be available to download. And then, so one last one, can you iterate over map keys and perform the same operation on each one?
Can you do it? I'm sorry, can you repeat that?
Can you iterate over different map keys and perform the same operation on each map?
Yeah, currently you cannot. That's one thing that you could do in predicate filters and predicate expressions, and you can't do here. And that is under consideration, but probably will not happen. So just so you know.
All right. So thank you. I think, yeah, we're out of time, but yes, please go and find us in the networking section, and hope you guys enjoy the rest of the summit. So thanks again, Ronen, and talk to you guys later.
Bye, everybody.